Hello and welcome to Enough of the Science. I'm Joe.
And I am Senan. How are you, Joe?
I'm not too bad. Looking forward to this week's episode. And for anybody who's joining us for the first time, basically Senan is a font of all knowledge when it comes to things scientific. And he tries to explain to my tiny brain what is actually going on in the world.
But the benefit of Joe having a tiny brain is I can tell him anything and he'd believe it.
Yeah, especially the nice stuff. I believe the nice stuff.
So Halloween is nearly upon us, so we should probably talk about monsters.
No, we shouldn't.
Why? Are you still worried about them in the darkness of the night? Do you hide under the bed covers?
They get worse as you get older. You think like kind of as soon as you stop being a kid, you stop believing in monsters. No, they become more real.
Wondering, is there something under my bed?
It's just what's going to get you.
Keep my toes in in case something reaches up from under the bed and grabs
What is going to get you? That's the question. What is going to get you eventually?
So the bad news is there really is monsters, so you were right to still believe in them. And there are millions of them, and they're worse than your worst nightmare. The things they can do to you is just, they can lock you up in an inescapable prison, they can burn you up, they can stretch you like a thin string of spaghetti. There's just so many horrible things they can do to you.
There's something wrong with your brain. There's something wrong with your mind. You know.
So the monsters we're talking about are black holes.
Aha! That was the longest segue into black holes I've ever heard in my life.
And the reason we're calling them monsters is they are the most extreme, largest objects out there in space.
They're the largest objects
that we know of, yeah. The largest single individual object.
So they're monstrous in size.
And they're also monstrous in their power. They have the most intense gravity you can imagine. And it's that really unbelievably intense gravity that actually makes them so interesting. And also is the source of all their horrible power.
And we don't really understand them.
We understand theoretically what they are, mostly thanks to the work of Einstein. But we better go back a little bit. So gravity, as I said, is their big attribute that they have. It's the big hammer they're holding behind their back, or the big sword they're swinging. I guess it was only when Einstein came along that the possibility that black holes might exist kind of became a real thing. Before that, our understanding.
People kept losing stuff. That's where all the stuff that you lose goes. The sock.
It's all in a big black hole somewhere. Yeah, and that must be a damn smelly black hole. So anyway, imagine before Einstein came along, our understanding of gravity was something like what I'm going to describe now, which is like, imagine two magnets on top of a table. You're holding them with your fingers, and as soon as you let them go, they pull towards each other. Now,
so it's an attraction of some
gravity.
kind.
Gravity is not magnetism, but that was kind of our understanding, that you had two objects that had some invisible force that pulled them together, right? So that there was an actual force involved. Like there is a force with magnetism, but there isn't, as Einstein discovered with gravity.
Okay.
So Einstein came up with this theory of general relativity, and essentially he discovered something, or invented or theorized something called space-time. He realized that space and time were actually two sides of the same coin.
Should have called it SPIME.
He could. Most of his work revolved around advanced mathematics, and his mathematics led him to believe that space-time was like a fabric, and that it could be warped or bent, or you could put dimples in it, or bowls, or whatever you want to call them. But he called it warping of space-time. And essentially any object that has mass causes some kind of a dimple or a warp in space-time.
Me.
Even you. You have a very, very small Joe-shaped dimple in space-time.
So I have a gravitational pull on tiny things.
See, you've got to get away from the idea of pull, because it's not a force. It's a warping of space-time.
I have a gravitational warp around me. I feel slightly more important now because of that.
And that basically what we observe as, two objects like the moon and the earth being pulled towards each other by gravity is actually a side effect of the fact that the space around those two objects is bent or warped or curved or whatever you want to call it. So what appears to be those two objects being pulled towards each other is just those two objects trying to travel in a straight line, but being forced into a curve by the warping of space-time.
And so the moon and the Earth. So the moon has its own gravitational
the moon,
warping.
The tides on Earth are caused by the moon.
By the warping of space-time.
Effectively, yeah. So the tides are trying to flow around the warped, bent bit of space
that the moon causes.
Yeah.
Oh, my head is beginning to hurt already. So if we can imagine, for example, the Earth has caused a bowl shape warping of the space-time fabric, and the moon is like one of those motorcycles in the circus that goes around the wall of death.
Yeah.
Because that, like the bowl is the wall of death, essentially.
Yeah. So the motorcyclist, from his point of view, is going in a straight line. But
Right.
it's just the surface he's riding on is in a curve.
Okay.
So from an outside observer looking at him, he's going in a curve. So that's a very good analogy actually for what's going on with the warping of space-time. Then when Einstein started following his mathematics to their ultimate conclusion, it appeared to him like it was possible for there to be what he called a singularity, like a point in space where there was infinite gravity, where the warping, the amount of mass that you could gather together in one point would be so much that you could cause infinite gravity, which didn't make any sense to him. And he that was essentially what started out as the theory of black holes, although he didn't believe it was physically possible to have that in space.
So obviously then the warp of space-time would just be so extreme that it would, I don't know, it's like a funnel or like a tunnel or a tube or like...
So I suppose the most famous attribute of black holes is that light can't escape from them.
Okay.
Right. That's probably that's kind of why they're called black holes. It's not that we don't really know what's going on inside in black holes. So we don't know that there's a hole in anything. It's the reason it's called a black hole is because light is falling into it and never gets out. So like it's the reason that happens is interesting, and it kind of buys or joins into Einstein's theory. So light is made from photons, like all electromagnetic radiation, be it radio waves or X-rays or whatever. And photons are known to be massless. They have no mass, no weight, effectively.
No religion.
Right? Indeed. And so in theory, if you assume, it's always been assumed since the time of Isaac Newton that the amount of mass that an object had determined how much gravity it had. Right, so the Earth is larger than the Moon, so its mass is greater than the Moon, so it pulls stronger than the Moon does, and so on. So that what follows from that is you would assume that if you have a particle which has no mass, like a photon, that's what light is made from, the gravity couldn't possibly affect it. It should be able to escape. But what's actually going on inside a black hole, according to Einstein's theories, is that...
I love the way you keep fobbing this off on him. This is all Einstein.
Yeah, he was.
If this is wrong, this is his doing.
Yeah, it's a clever tap. I wonder was he an alien came here to educate us about space? Anyway, he said that gravity was so incredibly intense in a black hole that space was warped almost into a complete circle, so that there was, once you went inside beyond what's called the event horizon, I'll come back to put a pin in that, I'll explain that in a minute.
Okay.
Once you went beyond the event horizon, which is near the black hole, that space became warped or bent so much that there was no path which led out. Every single path, even though the photons in there would be traveling in straight lines, the space was so warped that no path would lead out.
So they would just keep going round and round?
Well, they would eventually, all paths would lead in. All paths would bend around until they bent back towards the black hole.
Okay.
It's a bit like, I'm going to give you an analogy which isn't perfect, but it might help to understand it or visualize it.
You're overestimating me.
Imagine you've got a donut that's hollow. So it's a donut, but just with...
I can't imagine any other type of donut.
No, I don't mean the hole in the middle. I mean that bit where the dough is on the inside.
Okay.
Yeah.
So the inside of the dough.
It's a donut that's only got the crust.
Okay.
It hasn't got the soft dough on the inside. Right?
Yeah.
So imagine you're in there. If you think about it, every path leads back towards the middle of the donut. If you're on the inside surface, walking around on the inside surface of the donut, there's no path which leads out. They all curve back in towards the center, no matter which way you go. So it's kind of like that. Is what prevents light from. So it's not that the gravity is somehow pulling on the photons. It's that the photons, which are as far as they're concerned, like our motorcyclist a few minutes ago, as far as they're concerned, they're going in a straight line, but the surface they're on is curved, and every curve goes back towards the center. So that's kind of why light can't escape. It's essentially the geometry of curved space time.
Okay, and so and light is sucked in then as well.
Obviously, if light, imagine there's a beam of light traveling through space, minding its own business, and it encounters a black hole. Once it gets inside the event horizon, that's it. It's in.
Okay, the event horizon. There you go.
Yeah.
The event horizon is like the bouncer.
So the event horizon is not. It's kind of imagine it's like a sphere or a shell that's outside, away from the black hole. So the black hole is like a point in the middle of that sphere. But the event horizon is what we call the place where once you cross the event horizon, no light can escape. So that essentially means nothing. So light is the nothing can travel faster than light. So any event that occurs in there cannot be observed from outside, because light or any other form of information will not get out. So that's why it's called the event horizon.
So like when you look at an event horizon from a distance, it just is a blank space in space.
Yeah, yeah, and it's interesting. That's how kind of the first black hole was discovered. So Einstein didn't come up with the term black hole. There was another guy called Wheeler in 1967 who was kind of working on Einstein's theories and trying to,
Steal his ideas.
develop
I know
them
about
out
it,
a bit
yeah.
further. And he theorized that there might be a region of space with gravity so strong that light couldn't escape. And he said that, yeah, he called it a black hole. That was his term. And then it was only a few years, so that was 1967. But the actual first essentially proof or observation that tended to prove the existence of a black hole didn't happen until 1971. What's now called Cygnus X1, the X1 meaning it's the first black hole. So there was a
Because black hole begins with X.
X marks the spot. So there was a star they were observing, and it was orbiting in a very tight orbit around something they couldn't see. Now, you can if you're a scientist and you understand these things, once you understand how heavy, how much mass something has, and you know how fast it's traveling, if it's orbiting something, you can deduce the size of the thing it's orbiting based on how
So there's a formula for that.
yeah, or probably a very long one with lots of X's and Y's and J's and T's in it. Anyway, so they were observing the star, and it was obvious from the way it was behaving that it was orbiting something really enormous, like really, really something with a huge amount of mass, a huge amount of gravity, and yet they couldn't see anything. This star was apparently orbiting an empty area of space. So that was kind of the first proof that black holes did exist.
So it had to be, it was so big that it should have been visible, but they couldn't see anything.
Oh, I mean, if it was a star, it would have been really, really bright, much brighter than the other star they were looking at.
Yes.
So the only thing that might have had that amount of mass, that might have been that size, would have been maybe another very, very massive star. So that was kind of the first, and since then obviously we've found a lot of them, and there's some really interesting statistics about why they are monsters. So we have just since discovered that most galaxies have a black hole in the center of the galaxy that essentially everything else in the galaxy is orbiting around.
Most.
There's some galaxies that don't have that kind of shape of like the,
Oh, the spherical.
Yeah, that there's obviously things orbiting around in a circle, or an ellipse of some kind. The one that's at the center of our galaxy, we've called it Sagittarius A. It is 4 million times heavier than our sun. Right, so that's a pretty big object. Now, people might be wondering, how heavy is our sun? Our sun is 300 times heavier than the Earth. So,
okay, and so do the maths there.
4 million by 300. Our sun is 300,000 times heavier than the Earth. Did I say 300?
You said 300.
Apologies.
I thought, yeah. I thought, wow, it's only a little sun.
And so, it's Sagittarius A, our local black hole, for want of a better description, is absolutely enormous. 4 million times bigger than our sun.
Did we know where the center of our galaxy was before we found the black hole?
Yeah, I mean, it was obvious from observations that the galaxy was rotating around something.
Right.
But
we didn't know what. Could have been a pole or a...
Yeah, I didn't know what was the source of that. But I'm not finished there with the statistics. Some of the biggest black holes. Oh, good. You can't wait for the next statistic.
Oh, good. Let's
You're
go.
on the edge of your seat
Size.
there.
Let's go.
Some of the biggest black holes, based on what we've observed in the very far away universe, could be up to 50 billion times the weight of our sun. So that begs the question: how in God's name do these things form in the first place?
But it's just so unimaginable. You're dealing with numbers. Like, first of all, 1 billion, that's unimaginable. 50 billion, like the size of our sun is pretty unimaginable. And then multiplied by 50 billion, you're just kind of going, bleh.
Oh
Very
yeah. I
small,
mean, those are numbers our brains can't comprehend.
Yeah.
But just large, extremely
big.
large.
It's big. They're big lads.
Yeah. The definition of big.
Monstrous, if you will. If you're going to persist with this analogy for Halloween.
Well, you know, as a man of science, I try not to believe in monsters, but the evidence that they're there, unfortunately, exists. So how do they get formed in the first place? A star, they form from collapsing stars. Now, not every star ends up being a black hole. You've got to be bigger than a certain size. So we believe that a star has to be at least 20 times bigger than our sun before it's capable of creating a black hole at the end of its life.
Okay, that's kind of comforting.
So stars end their lives in various ways. Some of them go supernova, some of them turn into brown dwarfs, but some of them, by virtue of the amount of stuff that's in them, how big they are, will turn into black holes. And how that happens is interesting. So those stars typically might be a couple of million kilometers in diameter, and they're pretty big things. You know, even our sun is in the region of, I think it's about 300,000 kilometers in diameter. Anyway, the stars shine brightly because there is nuclear fusion taking place. So what's happening is there's an awful lot of material stuff gathered together in one tight ball, and the gravity that material has is so strong that it's squashing all the atoms together. And that causes something called fusion, which essentially means that lighter elements like hydrogen and helium are being squished together until they become heavier elements like carbon and various other things, silicon and what have you. The process of fusion releases energy, and that energy has outward pressure. So that pushes against the gravity that's trying to collapse all the material the star is made of. And they're evenly balanced. So while the star is burning throughout its lifetime, the amount of outward pressure from the fusion is balanced against the inward pressure from the gravity, and everything's hunky-dory, right? Everything is stable.
So it explodes things out and then drags them back in and squishes them down and then explodes them out again.
No, it's not a pulsing thing.
Right.
It's a smooth, continuous amount. So the fusion is taking place continuously, and there's a constant outward pressure caused by the energy from that fusion, and that's counteracting the inward pressure from the gravity, which is causing the fusion in the first place. But the point comes where the star runs out of fuel. In other words, all the helium and hydrogen and whatever else it is fusing is used up, right? Okay. And something really, really dramatic happens. Remember, we're talking about very big stars now, at least 20 times the size of the Earth's of our sun. In less than a second, from the point, it's like flicking a switch, from the point that the fuel is extinguished, the star collapses into a black hole. Less than a second.
And this is theoretical.
I believe they have observed it happening all right in distant stars.
It's like, it must be a light switch, like a big light switch, just going off. It's just like, it's there, everything's hunky-dory, then it's gone. Yeah.
Of course, its gravity is now multiplied because all that material that was spread over the full a couple of million kilometers that were the diameter of the star is now concentrated into an area, that's maybe only 1,000 or 2,000 kilometers. It's all being squished down, and that is what causes the intense gravity, because all that matter is now in such a small space. So they all the black holes start off as baby black holes, we'll call them. The mass of one star, be it a very big star, but relatively small. But what happens then, of course, is they have this huge intense gravity at their disposal, and anything that passes near them gets pulled in and gets added into the mass.
They don't get pulled in. Like kind of the warp in space-time, it's just like kind of it travels in a straight line
round. You were listening. That was a test. I wanted to make sure you were listening. So even other black holes. And actually, if I could digress for a minute, a few years ago, a very advanced experiment that was set up in the States called LIGO detected gravity waves. So that never before, it was theorized that there could be gravity waves passing through space-time, essentially ripples in space-time that were being propagated out like waves in the sea. But it was detected for the first time ever by LIGO a few years ago when two black holes merged. So what happened was, as they approached each other, their angular momentum meant that they didn't just smack together. They actually started orbiting each other tighter and tighter and tighter and tighter and tighter, and at ridiculous speeds. Like they were orbiting, remember, these things are big objects, and they might have been orbiting each other like 100 times a second. And that movement of two extremely dense gravity heavy bodies around each other created ripples that propagated out all across the universe. So this merger occurred like millions of light years away from here, but yet this detector was able to detect gravity waves for the first time ever, resulting from the merger of two black holes. So that's part of how they grow. They not only do they pull in stars and planets and any other dust or gas that they can find, but they will also pull in other black holes that are nearby.
Now, these gravity waves that were just in that particular experiment, like this is something that happened millions of years ago.
Oh yeah, they travel at the speed of light. So
Okay, yeah.
so if it was a million light years away, then the event would have happened a million years ago. Yeah. So and it's really interesting. Like, so how this LIGO experiment works is you've got two.
I'm just amazed that they could make this stuff out of Lego.
I should know what LIGO stands for. I can't remember. But
long, interesting, tracking.
Well, funny enough, long is features in it because you've got these really long tunnels, like hundreds of meters long. Two of them at right angles, actually a couple of kilometers long, I think. Two of them at right angles to each other, and they fire a laser beam from. There's a point where they meet, and they fire a laser beam up each tunnel. There's a mirror at the far end, and they measure how long it takes for the laser beam to come bounce back again. They know what the speed of light is. They know what it should be. So what happens when the gravity wave passes through our region of space is everything gets very, very slightly stretched or squeezed. Now we're talking about, say, the distance from here to the sun. It might alter the distance from here to the sun by like the width of a human hair. We're talking about a really tiny amount of, but in one of the tunnels, because the tunnels are at right angles from each other, one of them stretches a certain amount and the other one squeezes the same amount, and vice versa. So that's how we detect the waves passing through. So it's everything was momentarily stretched and squeezed, including you and I, when that gravity wave passed through.
This was it something that was just a wave passing through and they caught the wave, or was it a group of waves that like over several?
Oh, it was a set of waves. Yeah. So every time those two black holes before they merged orbited around each other,
they sent out
one wave went out, and then another one, then another one, then another one, then eventually and the waves they were able to detect the series of waves passing through, and they could measure them getting faster and faster and faster and faster because the black holes were getting closer to each other and spinning faster and faster and faster. So the waves.
So the guys who built these tunnels theorized.
Oh yeah, there was a theory that gravity waves were possible. Yeah. So that's why they built them. And since that, like, they have built more sensitive ones. I think that happened about 5 years ago. They've built more sensitive ones since, and they've detected plenty of other occurrences of gravity waves since.
Wow.
So and that's all. That's just one example of the extreme physics that black holes are presenting to us. So the event horizon, we spoke about that. Spaghettification. That's a scientific term, believe it or not.
Okay, you didn't make that up. Are you sure? I'm going to check that later.
So it refers to stretching. So the whole point of that word is that the gravity is so extreme around a black hole that there's a gradient of gravity, and there's a gradient of gravity anyway. So when you're near the Earth, the pull of the Earth is much stronger than when you're far away from the Earth. So the further away you get from any object, the less is the strength of its gravity. Its pull on you,
or the less warp is in the space.
Correct.
Fabric of space-time.
Yeah.
I think we should do. Yeah, I hate to have to correct you on these things.
Do you know what? I think the roles are reversed here. Off you go. You do the rest of it. So there's a gradient, right? But the gravity is so extreme around the black hole that the gradient is much tighter. So that means that, for example, there's a point, a smallish black hole, about 1,000 kilometers away from the black hole. The gradient gets so strong that there's a big difference between the amount of gravity that would be on your head versus your feet. So over a 2 meter length of an average human body, it would be much, if your feet are towards the black hole, it would be much stronger pull on your feet than on your head, and your body would start to stretch. And it would just keep stretching. Now, probably after it has stretched 20% or so, it would just disintegrate because your body isn't capable of stretching, and you'd probably be well dead by then. But
imagine this: like the stretching is the least of your worries if you're in that scenario.
But like if you were made from something that was much stretchier, like rubber or something, the stretching would just keep going. You'd be stretched out into a long string of spaghetti.
And has anybody ever survived this?
Nobody that we know of has ever fallen into a black hole. Thankfully, there's none anywhere near us that we know of. As I said, the one at the centre of the nearest I think that we know about is Sagittarius A at the centre of our galaxy, and that is about 25,000 light years away from us. So it's a long way.
You'd think that was a safe distance, you would think.
Yeah. So how do we've realised there's an easier way of observing black holes than just seeing what it's doing to some star that happens to be going around it.
In movies. You can watch them in movies.
That's true. Like Interstellar. And that is something called an accretion disk. So,
oh wow, because we were talking all about secretions last week.
Accretion. Yay.
Accretion disk.
A secretion disk is a big different thing, I think. So an accretion disk, so it accretes material. So it's the stuff that's going to fall into the black hole usually doesn't fall straight in, because it's traveling through space at an angle to the black hole, and suddenly it comes within the influence of the gravity and it starts to curve around and it goes into a kind of an orbit around the black hole, and it spirals in until it eventually is going to fall in and become part of the black hole. But it spends quite a long time rotating around, orbiting around. So you've got this, what happens is this disk of material builds up in orbit around the black hole, all the stuff it's sucking in. And the huge gravity involved starts accelerating that stuff. So it starts to move faster and faster and faster as it moves in towards the black hole. And you get a lot of friction. It starts hitting off, all the bits and pieces of it start hitting off each other. If there's planets or stars involved, they probably have their own magnetic field. So all that magnetism is churning around in there as well. And there's a real maelstrom of chaos. And the material heats up enormously. It heats up to millions of degrees and starts to glow.
So this is visible then?
Yeah, so we see this, we have directly imaged at least one black hole by looking at this dull orangey red ring around it. So that's a new way for us to observe black holes. And the accretion disks, like the heat, and they're emitting X-rays, they're emitting all kinds of radiation because of the extreme violence of what's going on in there.
And does the accretion disk, is that a feature of every black hole, or they burn out after a while? Or
well, any black hole that is sucking in any significant amount of material is going to have an accretion disk. Now, some black holes are probably in places where there's nothing near them, and then you don't. Like, you know, you wouldn't see that. You wouldn't know it was there unless you were able to observe the effect it was having on some other nearby object. So yeah, and those accretion disks are they actually, another one of Einstein's theories is that matter and energy are just two different forms of the same thing, and they're actually able to convert up to about 40% of their matter into pure energy that radiates away as X-rays or whatever before it falls into the black hole. Like, there's so much violence going on in those accretion disks.
So the accretion disk is outside the event horizon?
Yes, correct. Yeah. Because we wouldn't see it if it was inside it. Now, there's probably a part of it inside the event horizon that we can't see. You know. So that's another very interesting piece of physics that's involved. And then you've got these things called relativistic jets, which are something that occurs at the poles of some black holes. Now, it's still outside the event horizon. So it's material from the accretion disks that is interacting with the magnetic field. Now, this is highly theoretical. They're not well understood. But
that's not narrowing down the topic today.
But
there's a lot of things that are not well understood today.
They've been observed, people can see them, but the reason how they occur is not fully understood. Essentially, they're like a beam of particles, of high energy particles, that's like a lighthouse shining out of the pole and the north and south pole of the black hole. By pole, I mean, so pretty much every object in space is spinning, and black holes are spinning too. So the poles are obviously the top and bottom in relation to the spin. It's theorized that the extremely strong rotating magnetic field of a black hole at its poles is interacting with the material in the accretion disk and is accelerating it up to over 90% of the speed of light. It's the fastest. Obviously, photons, light travels at light speed, but anything that has mass, and these particles that are in the accretion disk have mass, they're being accelerated up to 90% of the speed of light. It's incredible. It's the fastest moving things in the universe, like really incredibly fast.
Over huge distances.
And they're squirted out over massive distances, like thousands of light years. Some of them could be squirted out from the north and south poles of
And can they use this to detect black holes then?
Good question. I'm not sure how they observed them. I'm not sure how, but perhaps. But we're getting beyond the edge of my event horizon now.
Yes.
There,
You do know, you just can't give us the information.
so there's just so much fantastic physics going on around black holes. They are our theories, which are based on Einstein's general relativity. The mathematics just breaks down when you get into the region of a black hole. So they really are a mystery for physicists, because our understanding of physics that we can see in operation in the rest of the universe just doesn't occur inside the black hole. There's something weird going on in there. It's theorized that we might need something called a quantum theory of gravity to explain what we see going on inside black holes, or what seems to be going on in there. And there's just so many other things that I didn't touch on, called, for example, Hawking radiation, which is essentially a theory that says the black holes will gradually evaporate. Even though originally we thought nothing could escape from a black hole, this theory is now accepted as very likely to be true, and that very slowly that black holes evaporate particles off their surfaces.
Back into space.
But it would take trillions of years for one to actually completely evaporate.
So what would happen if I was out for a stroll in one of the nether regions of space and happened to walk into an event horizon?
What would happen? Once you cross the event horizon, that's it. You're not coming out.
Right. So it's like a bar?
From the point of view of an outside observer, because of the warping of space-time, remember I said Einstein established that space and time were both two sides of the same coin. Because of the warping of space-time, an outside observer not at the event horizon watching you fall towards it would see you slow down until when you reach the event horizon you would freeze, just solid, and you would then kind of turn a weird red colour and fade away slowly into nothingness. From your point of view, none of that would happen. You wouldn't be aware of any slowing down. You would not be aware of any freezing. You would cross the event horizon. Everything would feel normal to you, and you would continue on towards the black hole. Now, at some point, depending on how big the black hole is, you would be spaghettified by the extreme gravity. Either that or cooked by the accretion disk.
Okay.
But,
the spaghetti analogy just keeps giving.
Yeah. So it's weird that time effectively from the point of view of an outside observer stops at the event horizon, whereas for the person at the event horizon it doesn't. All down to the warping of space time.
Speaking of time stopping, I think it might be time to stop this episode of Enough with the Science.
Yes, indeed. We've probably done enough time bending for today. And, hey, if you've got any energy left by the time you have finished listening to us, maybe you might give us a review on your favourite podcasting platform. It really helps us.
And do join us next time on Enough with the Science. We're going to fade away over our event horizon now. Bye.
Yes, I can see the black hole coming. Have a nice day.